Okay, now let's do one more example. Now, if you remember last week, we had discussed how we can discharge a capacitor through a resistor. Now let's discuss how we can charge a capacitor using a battery. And then we will continue with your questions. So this will be the circuit we will discuss. We have a capacitor. We also have a resistor. And both are connected in series to a battery. So let's say this has capacitance R, this has resistance, capacitance C, resistance R, and the EMF epsilon. Well, there's a single current running through the wire. We also need to decide what we mean by a positive charge of the capacitor. And I will say that the capacitor is positively charged if the left plate is positively charged. Let's say it's charged at a given instant is Q. Let's start with this point. What is the potential drop from this point to this point? From this point to the other point? Plus or minus? Because as we go from this point to this point, we are going from the positive plate to the negative plate, so that's the potential drop. From this point to this point, is it plus or minus? Plus. You are running in the positive direction of the current. And from this point to this point, from here to here, minus epsilon. This is equal to 0. This is one equation we have. How many unknowns we have? 3. What are they? Q is an unknown. We have to determine as a function of time. I is an unknown which we have to determine as a function of time. That's it. R is a given. It's the resistance you choose for your circuit. C is a capacitance that you choose for your circuit. Epsilon is the EMF of the battery that you choose for your circuit. So in principle, when you are constructing your circuit, you know R, you know C, and you know epsilon. What you do not know is how Q or I changes as a function of time. So those two are our unknowns. Now, the next thing we have to do is we have to relate Q and I. So QI is dQ by dt, but positive or negative? It's positive, because if you see, if I is positive, that is the current is running in this direction, the charge on the positive plate will increase. So as it's increasing for positive I, dQ over dt is positive if I is positive, so the sign is positive. Let's just place this in the above expression, and we get a single equation for the single unknown Q. So Q over C plus dQ by dt times R minus epsilon, this is equal to 0. Now we have to solve this equation. Now last week we had the first example of what's called a first order, and because there is the first derivative only, the first order differential equation, we just gave up the solution, but we can actually derive the solution for these first order differential equations. Let's see, I can write this in this form. dQ, well, let me first write it in this form, dQ over T plus 1 over RC times Q. This should be equal to epsilon. Or dQ should be equal to epsilon minus Q over RC times dt. So if I wait a very small amount of time dt, when the charge in my capacitor is Q, the change in my capacitor in this amount of time dt will be given by this expression. Do you agree? So let's just let me also rewrite it in this form, dQ by divided by epsilon minus Q over RC. This should be equal to dt. So this just relates the change in time to the change in charge. But I can just, if this relation holds for any time, I can just sum all these changes from some initial time to some final time. But that sum is nothing but what we call the integral. So let's see, at the time, let's start from t is equal to 0. Up to a final time, let's call it t. And in this time, as time goes from 0 to t, the charge, let's say it starts from some initial charge, q0, up to a final charge, q at the time t. So we are just summing these both sides from some initial value to some final value. Okay, what is the integral on the left? It is one of your favorites. It's the logarithm of epsilon minus q over rc divided by minus 1 over rc. And q starts from q0 up to q at the time t. This is the left-hand side. Now the right-hand side, it's just t. Do you agree? Yes, no? Do you agree? Now what this symbol means is that I have to replace this q by q of t and subtract what I obtain when I replace q by q0. Logarithm of epsilon minus q over rc, q of t over rc, minus the logarithm of epsilon minus q0 over rc. This should be equal to minus t over rc. And what is left is you have to solve for q of t. I will just write the result. Well, let's solve it. So you remember the properties of the logarithm? So this is nothing but logarithm of epsilon minus q of t over rc divided by epsilon minus q0 over rc. This should be equal to minus t over rc. And if you remember, we had defined this rc to be the time constant tau when we were discharging the capacitor. This is the time it takes for the capacitor to discharge a significant portion of its initial charge. So we will use the same notation. So epsilon minus qt over tau divided by epsilon minus q0 over tau. This is equal to minus t over tau. E to the power minus t over tau. So q of t over tau will be equal to q0 over tau minus epsilon e to the power minus t over tau minus epsilon. Do you agree? So what I did is, well, I just multiplied both sides by a minus sign. I multiplied this with this one. It is this term over here. And then I should add this. This is plus. So let me just write q of t. This is equal to q0 times e to the power minus t over tau plus epsilon times tau times 1 minus e to the power minus t over tau. Well, q0 is 0. Initially, the capacitor is not charged. So Q of t, the charge in the capacitor as we are charging it from 0 initial charge, is just epsilon times tau times 1 minus e to the power minus t over tau. Well, I made one mistake. Here, this is epsilon over r. Epsilon over r, epsilon over r. So here, this is epsilon over r. This is epsilon over r, epsilon over r. Where? Oh, yeah. Now, let's see, does this make sense? Okay, we solved the mathematics. So this is what we found for the charge at the time t. So let's see. We said that initially the capacitor is not charged, so at t equal to 0, the charge should be 0. Is this true? Okay, so if we put t is equal to 0, e to the power 0 is 1, 1 minus 1 is 0. Okay, in that sense it makes sense. Now let's see what will happen if you look at the circuit. Initially there is no potential difference across here. So the potential difference that the battery creates should all be across this one. So initially we should have the current equal to epsilon over r, because there is no potential drop over here at t equal to 0. It's not charged. There is no potential drop. The potential across the resistor is just epsilon created by the battery. So at t equal to 0, the current should be epsilon over r. Okay, that is one thing we should check. Now, as the current is running, there will be charge building up over here in the capacitor. As the charge is building up over the capacitor, there will be a potential drop across the capacitor. But that means there will be a smaller potential drop across the resistor. But a smaller drop across the resistor just means that the current will get smaller and smaller, until all the potential difference created by epsilon is across the capacitor. There won't be any potential drop across the resistor, but just that means there won't be any current running through the system. So if we wait long enough, epsilon will be equal to the potential drop across the capacitor, which is Q final, whatever the final value is, Q final over C. So Q final should be just epsilon times C. So that is something we can check. Well, we already checked that Q at t equal to 0. This is equal to 0. Q as t goes to infinity, e to the some minus very large number is 0. So this is just 1. So we are left with epsilon tau over r. But remember the definition of tau. It was epsilon, tau is r times c divided by r. This is epsilon times c. So this is what we had expected at t goes to infinity. The charge in the capacitor should be epsilon times c, and that's what we obtained. Now the last thing we can check is the current. We said that initially the current should be just epsilon over r, because there won't be any potential drop across the capacitor. Now we should calculate the current. Now we have the relation between the current and the charge. The current is nothing but dq by dt. I is equal to dq by dt. This is equal to epsilon tau over r. The derivative of 1 is 0. And the derivative of that exponent is nothing but minus 1 over tau, e to the power minus t over tau. This minus minus makes plus. This is equal to epsilon over r, e to the power minus t over tau. This is the current. So you say at t equal to 0, initially when the capacitor is not charged, this is just 1. the current that is running through the battery is just epsilon over R. So we see that, in a sense, an empty capacitor, at least for an instant, as long as it remains empty, it is just like a short circuit. It doesn't change anything. It doesn't influence anything. At least it's just for a short time until it acquires some charge. When it acquires some charge, it will resist the current. But until that time, at t equal to 0, this is not charged. It just acts as if it is not there. And the current is just epsilon over R. Now, it will be especially important when we have current that changes its direction. Now, we will study alternating currents later on, but there we will see that if the current is changing its direction very fast, before the capacitor can build up any significant current, it will be as if the capacitor is just empty. It's just a short circuit. Now, any questions on this solution? How we obtain the solution, how we interpret the solution? Well, let's see how I changes as a function of time. This is initial current, which is epsilon over R. So with time, it just decays exponentially. So this is how it will look. Tau is over here when the value of the current is I0 over E. It's almost 1/3. E is just a number that is something like 2.7. So tau is the time it takes for the current to reach almost 1/3 its initial value. Or if we are discharging the capacitor, it was the time it takes for the charge in the capacitor to go to its 1/3 value. Now, another important parameter will be the half-life. So, in your experiments, did you study the half-life? Now, you will be studying the half-life. For example, half-life of this current, it will be somewhere over here. It is the value at which the current is half its initial value. So it's defined as e to the power minus t1/2 over tau. This should be equal to 1/2. Just take the logarithm of both sides. So since they are equal numbers, their logarithms should also be equal. But this tells you that minus t1/2 over tau, this should be equal to minus the logarithm of 2. And t1/2, well, let's say, let me add one more step. Logarithm of 1/2, which is minus the logarithm of 2. So t1/2 is equal to tau times the logarithm of 2. So the half-life and this time constant, basically they carry the same information. It's just how you define it, and they are related by this relation. Questions? If we look at how the charge changes as a function of time. You see, initially, this has its maximum value. At t equal to 0, it's 1. So the Q is 0. As time goes on, this becomes smaller and smaller. So you are subtracting a smaller number from 1. So Q keeps increasing. It will approach its maximum value, but exponentially. Let's say this is Q max. So this is how it will change as a function of time. So it will increase. Well, if you look at this expression, it takes infinite amount of time to reach the maximum value, but in practical applications, after a couple of tau, you will not be able to see the difference. No, ideally, it never reaches the maximum value. But, I mean, if you wait, I don't know, at this point, which let's say is 2, 3 tau, you cannot really see the difference between the actual charge and its maximum value. The difference will be, you will not be able to measure it. So in practice, you can say that it did reach the maximum value. And when you do the experiment, it will probably be more clear. I mean, you will really see that it just becomes flat. Well, the maximum value is this one when this exponent is 0. But this exponent is really only if t is equal to infinity. And t is never infinite. You will just wait at most a few seconds. Now it will, whatever the capacitance is, it will never actually reach that value, but the difference you will not be able to measure it after a couple of tau. Well, you see, you will be scientists. Okay, if you look at the history of science, scientists study things that they don't know. So there's always this argument whether the lab course should be in synchrony with the theory course or not. I am one of the defenders that the lab course should go ahead. So you should have the problem first that we can study in the classroom.
Should at least have some idea of what we're doing.
Don't become an experimentalist. Other questions? Not necessarily about this example, but about any questions on the circuits, how we determine the signs, etc. How we write the equations that will allow us to determine the unknowns. What do you mean? Okay. I mean, if I had started by choosing this plate to be the negative plate, I would have ended up with the solution. Sure. But, I mean, in this simple circuit at least, the charge will always have the same sign, and which will depend on your convention. It won't become positive, then negative, positive, and negative. It will not change sign. In this circuit, we will see circuits in which the charge changes sign, but not in the simple one. And depending on your convention, that sign you can just take to be positive or negative. Other questions?
Why actually the Q is the maximum, but in the circuit itself, what is the capacitor gauge when reaching t equals to infinity?
Now, t is just the time that you are measuring.
Okay. You said here, like, when t goes to infinity, the charge inside the capacitor will be a maximum. That's why it will be causing for the current itself if you are moving above.
The other current.
No, I'm talking about the equation of the current. Yeah. The equation of current here will be equal to 0. Right?
True. You see, the current is the derivative of this charge. It's the slope of this line. At this point, the slope is this one, so that is your current. At this point, the slope is almost horizontal, so the slope is 0. So your current is also 0 at this point. Questions? There were some questions before the break.
It's not related to what means by isotropic in
It's quite off the topic. Come to me after the class. Let's see, I have some questions for you then. Just a few review questions. So we have an ideal battery. It is connected to a light bulb. Then you connect a second light bulb in parallel to the first one. So how does the power output from the battery change? So it's the same battery. Rather than connecting one light bulb, you connect two of them. So how does it change? Okay, I will repeat the question in Turkish if you don't mind. Bir tane pilimiz var. Pile bir tane lamba bağlıyoruz. Belli bir power output'u var. İkinci bir lambayı paralel olarak bağlıyoruz. Pilin power output'u ne olur? Artar mı, azalır mı, değişmez mi? 1/4'e mi iner? 2 katına mı çıkar? Come on, there are only 30 answers yet. I cannot send. Okay, so let's see. The majority is B, C, or D. Twice the same, half. So nobody went to one, well, there are a few that went to 1/4 as much. Nobody 4 times higher, and nobody went for, don't know. Okay, why B? There are like 17 people who said that it will be twice as high, the power output. Why? Okay, I will repeat in English. Okay, so what he says is that the potential, the voltage of the battery, the EMF of the battery is constant. The equivalent resistance is just halved because you are connecting two resistors in parallel. So the current is twice. The power is nothing but the EMF times the current. Since the current is twice, so the power output of the battery is twice higher. So that is his explanation. Anybody who answered B or C who wants to oppose him? Nobody? You are all convinced with his explanations? Shall we vote again? Now, anybody wants to oppose him? No, he said that it was B. So you think it's not B?
I think it's C because generally when we look at batteries, it says power output. That doesn't change.
So the power output doesn't change in batteries. That's his claim. No, we are not talking about the power dissipated. We are talking about the power of the power output of the battery. The power output from the battery. We are not looking at the power dissipated. It's the same, it doesn't change. Does anybody have a battery?
I have a battery that has the same voltage.
Okay.
And I put another resistance. It has a value of I at the beginning, at the first term. When I add another resistance, the resistance is increased, is decreased, and the current is decreased.
So you are saying the resistance decreases and hence the current decreases. Well, let's see, first of all, if the resistance decreases, the current, does it decrease or increase?
V is constant.
Okay,
R is
decreasing, so I should increase. Okay, resistance decrease, I increase. And hence?
we will use the value of V of I out, which is equal to V squared over R. R is
So, okay. Let's see, what you're saying is this one. What your friend is saying is R goes to R over 2. And hence, I, which is V over R, goes to 2I. He says that P is equal to I times R, I times epsilon, I times V. V is equal to I times R. This is I squared R. I is doubled. I squared is 4 multiplied by 4, so the power is 4 times more.
But R is
R?
R goes to R over 2.
So you are saying that this goes to 2I squared times R over 2. But isn't this the R of the battery? Okay, so don't get confused. What is the power? The power of the battery. An ideal battery. Power is equal to I times epsilon. the EMF of the battery. That's it. Epsilon is not equal to V times I times R. Because epsilon, now the potential drop across a resistor is just I times R. This is not the potential drop across a resistor in general. This is the EMF of the battery, and it's just for a given battery that is just fixed. You cannot do anything else with this one. You cannot just replace epsilon by I times R. No, it's not true. It doesn't exist. Epsilon is just epsilon. It is fixed over there. Now, the power dissipated by a resistor now, this is P is equal to I times V. In this expression, V is the potential difference across a resistor. And hence, we also know that the potential difference across a resistor is I times R. Or you can also say that the current running through a battery is nothing but the potential difference across a resistor is the potential difference across the resistor divided by R. These are all valid. If you have a single battery and a single resistor, of course, energy conservation tells you that the power of the battery should be equal to the power dissipated by the resistor. Then only in that case these two things will be equal, not because epsilon is equal to IV in IR, not epsilon is equal to IR in general. Epsilon is just, for a battery, epsilon is just epsilon. It's okay, what about the power? Your friend was claiming that on the battery it says that the power output is constant. Does anybody have a battery? No. Something that he can show me where it says that the power output is constant. Did you get your battery? Now, is this difference clear? Epsilon in general is not I times some resistance. Only the potential difference across a resistor is I times R. Epsilon is the constant. EMF of a battery is constant. Now, the actual potential difference that you measure across a battery, it will depend on the current running through your battery. Because the actual battery will be an EMF source, which is constant, and a resistor. So there will be a potential drop across the internal resistance of the resistor. Now bring that adapter when we discuss alternating currents. Okay, any questions on this question?
What is the answer?
Well, I is halved. Now I is doubled. There's double current. I is doubled. Epsilon is constant. Power is doubled. Well, you can also think of it in terms of the energy conservation. You see, battery, when you connect resistors in parallel, we have two identical resistors in parallel. Each one, the potential across the resistor will be the same. It will be equal to the EMF provided by the battery. V is constant. R, we have two batteries that have the same R, so the power of each one of the light bulbs will be the same. Well, we have two of them in parallel, so the power dissipated by both of the light bulbs is twice the initial value. And that power comes from the battery, so the battery should provide twice the power.
So light bulbs cost
No, they will not become brighter. Each one will, in fact, each light bulb will be just as if the other one doesn't exist. But since we have two of them, both of them combined is brighter. So let's see. Okay, you should be answering this fast. This is just something we discussed, let's say, in 10 minutes ago. Okay, I will just pass this question so we can discuss another one. If you wait long enough, the current just goes to zero. It's almost zero, so the answer is A. Most of you got it A. Now, any questions on this one from those who said B, C, or D? Why were you confused? Any volunteers? Why you thought it was not zero? Yes? No. Your friend is asking why can it become nearly constant but non-zero? Not really, because you see, if the current was constant, or nearly constant, almost a constant, let's say it's a constant, so there will be a buildup of charges on the capacitor. So it will keep building up. But if it keeps building up, it means that the potential difference across the battery will also keep increasing. Well, it will be maybe increasing slowly, but it will constantly keep increasing indefinitely. But the potential difference across the capacitor cannot be larger than the potential difference provided by the battery. So it cannot be nearly constant. Okay, I don't have any more questions for you. Yeah. After you do the quiz, you can go. That is milliampere. The current R is 2 ohms, so what is the power dissipated?
Dissipated power.
Dissipated power by the battery.